Okay, thank you, Jan. Good morning, everybody, and thank you for coming this early to the talk. So in this talk, can you hear me in the back? Okay, so in this talk, I'll give some insights on what I think is a very important topic, which is interdisciplinary research at the time of pervasive changes. This talk will be given in English, in Chinese, and in Korean. Okay, I'm kidding. It's only going to be in English. Come on. Okay, so the talk will be given in English. And so let me start first by pointing out some trends that I observe in the computer architecture community. And I think the same may occur in the PPOP and HPCA. So the first one is that our community is growing. So we used to be few people in the past, and now we have much bigger community, a much bigger community. And this appears, for example, in the attendance to conferences. So what I did is I went back to ISCA 2010 as a sample point, and we had there 430 attendees. And this year we had 821 attendees. So we nearly doubled the number of people in 9 years. At the same time, our communities are becoming more and more international. So going back to 2010, the number of countries that had papers in ISCA, there were only 4 countries. And this year, we had many more countries represented in the ISCA. So that's very good. Also, if we look at the number of papers submitted and accepted, hopefully accepted too, have increased a lot. So I went back to every year of ISCA and I counted the number of submissions and the number of accepted papers. So what you can see here is that we started, let's see if I can get, do you guys see the mouse? Mm-hmm. Okay, so we started with 250 submissions back in 2010, and now we are over 420 submissions. So submissions increase very quickly, and you can also see that the acceptance not so much, but hopefully this time it's going to go up. So that's a trend. And another trend that is very important is that if you look at the topics that people are working on, it's becoming very broad. It's actually mind-boggling to go to one of these conferences and try to understand all the papers that are being presented there. So what I did is I went back to ISCA 2010 and I listed all the session titles, right? So we have caches, energy efficiency, multi-cores, right? So this is what we had in 2019. We had using AI to improve architecture, non-traditional workload domains, deep learning and AI, quantum, so much more. Right? So that's why the title, that it's a time of pervasive changes. So overall, we have communities that are increasing quickly, right? We have many more submissions, we have a lot of international attendance, and we are broadening the areas of interest. Unfortunately, at the same time, we are seeing that funding in computer architecture is flat. In fact, it's going down a little bit. So what I did is I went to the SAIS website, okay, from NSF. So you may know, those in the US, that SAIS is the directorate of NSF that funds computer science, right? And I looked at the documents there, and this is a public domain document, the budget of SAIS, the appropriations over time. So you can see here that the budgets are flat, right? In fact, this increase in 2013 maybe because SAIS absorbed the supercomputing division. Okay, I think that's the reason, I'm not certain. But I think the high-level idea is that funding is flat. Moreover, funding is moving away from core programs. Okay, those in the US know that core programs are the parts of NSF that fund basically the general parts of architecture, compilers, operating systems, right? So I looked at this document, which is also in the website of SAIS, which is for the requested funds of 2010 some important items. Remember that the budget is about 850 million for 2020. 300 are for AI. Okay? So that's, and it's increasing 8% over 2018. Quantum and information sciences, 15 million, that's a 53% increase in 2 years. And there's some other stuff here. So we need to keep this in mind. This is something that is going on now. And also that there is a big emphasis on interdisciplinary research. So you may know that most recently, NSF has posted this new call for proposals, which by the way, I'll do very soon, at the end of next month. So this is the principles and practice of scalable systems, which specifically requests funds or requests proposals that are highly interdisciplinary. You need to have 4 people from 4 different areas to work together and get this award. Right? So the high-level idea then is that funding is remaining more or less flat. In fact, it's going towards more other areas that are away from the core and more interdisciplinary. So what should we do as researchers in this environment? How do we react to this? So my pitch in this talk will be that we need to focus on building interdisciplinary research teams. So if you're a faculty, try to find colleagues in your institution or maybe in other institutions who have complementary expertise and build a interdisciplinary team. And if you're a student, work with more than one faculty member so that you can benefit from the two. So the reason for this, I think, is that this is potentially the most impactful research that we can do at this point, because you're going to address, with this interdisciplinary team, you're going to address a problem that nobody can address by itself, right? So you have an advantage because you work with multiple areas. And second, it is most cost effective because you can gain insight by picking the brain of some other researchers who have spent their lifetimes or many years becoming an expert in this area. And in addition, this type of research is very consistent with the trends that I just outlined. Because we are many more people in the community, we are looking at many more topics, and it's going to be to your advantage to look at a problem that only you can solve, because you have a certain expertise that combines multiple domains. And also, as I said, it's consistent with the funding trends that NSF and possibly other agencies are pursuing. Okay? So many areas are actually at this point ripe for interdisciplinary research. I have listed here just a few, but I'm sure that many of you, both faculty and students and researchers, can come up with. So for example, combining computer architecture and security is a very hot topic. You can develop secure architectures. Combining programming and computer architecture, you can work on programming non-volatile memories or programming accelerators. Combining operating systems and computer architecture, there's lots of new virtualization technologies that can take advantage of somebody who knows about both areas. Computer architecture and algorithms, you can work on accelerating machine learning. Computer architecture and circuits, 3D stacking of processors. Computer architecture and bio, genome analysis. Computer architecture and communications, wireless architectures, EM attacks, and you name it, many, many different things. In the rest of the talk, I'm going to focus on just 2, which are the areas that I have been working on in the last few years. And maybe I can give you some insight on what were the advantages or how I work synergistically with other faculty who have complementary expertise. So I'm going to talk about rethinking hardware for security. This is where I'm going to spend the majority of the talk, really. And then redesigning virtual memory translations from scratch. So let me start with the issue of rethinking hardware for security. as architects, we know about, what do we know best? We know about caches. Okay, so all of you know about, all the HPCA attendees know about caches. We know about coherence, at least a big chunk of us, right? And we have been brought up with these principles, which is make the common case fast, share resources between the different processes, right? Prefetch and speculate. So we certainly know about speculation. But then talking to my friends in security, the first thing they said is, but these are precisely the principles that you should not do when you do secure architectures. Huh? So we said, how come? All this needs to be rethought. Indeed, in the process of thinking about this, we heard about this speculative attacks, Spectre and Meltdown, and really we saw that speculation is a big problem. So because of that, we talked and said, okay, let's work together and build on each other's expertise, and we worked on speculation attacks and replay attacks. So the professors I work with are Professor Chris Fletcher, Darko Marinov, and Adam Morrison, which have complementary expertise to mine. And of course, the ones who do the work are the students, Mingia and Dimitris. We just scheduled the rooms for the meetings. Okay? So let me speak a little bit about the speculation attacks and the replay attacks. I'm going to try to emphasize the places where I helped them and they had helped me. Okay? So the background of this is a speculative execution attacks. These attacks exploit the side effects of transient instructions. Transient instructions are those that are executed speculatively and that eventually will be squashed. The best example is this one here, where you have an if statement that you pass an X, and this X will be compared against the bounds of an array. Now, I'm going to pass a very high value of X that should fail, but the branch predictor predicts that it's going to be okay. And so inside, let's see if I can find the cursor here. I don't seem to find the cursor. Anyway, so the X here is used, oh, you see?
It's gone.
Move it. There it is, top, very top right.
Oh, you see. So you pass the X and you index an array, you get a value, and then you use the value to address as an address to the second array. So if there's an attacker that actually reads the address, it knows the value that was in this first array. Right? So these are transient instructions. And this is a typical example, this is a Spectre attack that uses control flow speculation. Now, architects know about speculation. So when we saw this, we said, wait a second, speculation occurs not just because of branches, but it is widespread, right, in a processor. A load, in fact, a load is speculative all the way until it reaches the head of the reorder buffer. Therefore, it is vulnerable to any speculative attack. So we came up with this comprehensive model that includes not just branch mispredictions, but any sources of transient instructions. For example, in addition to control flow speculation, we have exceptions, which when you squash, these are transient instructions. Address alias between a load and an early store, aliasing between two loads, memory consistency model violations, interrupts. So all these are potential vulnerabilities, and therefore it's possible that in the future we will see attacks that address this problem. So how do we go about defending against this thing? So we start with a model, and the model is, let's look at the lifetime of a load instruction. At the beginning, a load is issued to memory speculatively, and it remains speculative until it reaches the head of the reorder buffer. Now, in the Spectre attack model, where we only care about branch mispredictions, a load is unsafe until the point where all the older branches before the load get resolved. So at this point, when all the branches that are older than the load get resolved, the load becomes safe. in this comprehensive attack model that I just described, the load remains unsafe until the point where it cannot be squashed anymore, right? Therefore, it means at the point where neither the load itself nor any older instruction in the reorder buffer can suffer exceptions, control flow mispredictions, address alias, squashes, memory consistency violations, or inerrors. We call this point where you cannot suffer or the load becomes safe the visibility point of the load. Okay? So the visibility point will depend on your attack model. So how do we defend against speculative attacks? There is a trivial approach, which is we wait to issue the load until it reaches its visibility point. Right? So we would have something like this. The load could be issued here, but we're going to wait until we reach the visibility point, and then we issue the load. But it's a big problem. The problem is that loads then are issued much later than in a conventional processor. Moreover, if we're looking at the comprehensive attack model, we cannot issue the load until it gets very, very close to the head of the reorder buffer, which means that effectively we have an in-order processor. So that's also not a good solution. We have to come up with a way to issue the load earlier, but safely. So the approach that we proposed, that's just one approach, it's called InvisiSpec. And the idea is that we issue the load as soon as possible, like in a current machine, but we issue it invisibly. That is, we cannot make any changes to the cache hierarchy. Right? So this would be the idea. And then, when the load reaches the visibility point, then the hardware will do a second access that will refresh the memory subsystem, setting the states and bringing the line into the cache and so on. Okay? So this will be the idea. The load will be issued invisibly. It will use the data and pass the data down the pipeline to any instruction that follows. And then when you reach the visibility point, the hardware issues a refresh transaction to make it visible to the rest of the world. Huh? This is very good because then speculative loads can be issued as early as in a conventional machine and can pass the data to the dependent instructions immediately. The problem is that you need to support an invisible transaction that does not change the status of the caches. Okay? So that's the challenge. And so how do we make loads invisible? Well, we need to issue an invisible request somehow, a load that brings the data but doesn't change anything. And then talking to the security experts, they said, you cannot change anything. You cannot change the cache occupancy, neither yours nor any cache in the system. You cannot touch any replacement information, the replacement bits, LRU bits, cannot do anything. Cache coherent information you cannot change. No TLB state. So we had a lot of discussions, and it has to be something that is invisible, really. So we bring the data into a speculative buffer in the processor. Okay? We don't load it into the L1, and we pass it to the register. Okay? So that's the idea. There are lots of details, but that's what you need to do ideally. So what happens? How do we make the load visible? So we know how to keep it invisible for a while. We bring the data from wherever it is without changing the coherence states. Where the data is, bring it into this buffer and to the register. What do we do at the visibility point? At this point, the hardware has to use this refresh request, which will change the cache state and everything. From the time the load was issued invisibly until it makes the request visible is what we call the window of invisibility. Okay? For a given load, a load has a window of invisibility. During this time, if somebody else writes to this location, the processor will not receive an invalidation. It will not know, because the writer doesn't know that you have a copy, so you will not receive an invalidation. Okay, so architects know that if this happens, we have a problem. If you don't see an invalidation, we have the problem that you risk violating the memory consistency. Okay? So how do we solve this problem? And this is going to be the only complicated slide in the talk, so bear with me. There are 2 slides and they're a bit tricky. So how do we solve the problem? So first I'm going to give you an example of how memory consistency is violated. Suppose I have a processor P1 that tries to read a lock and then a counter inside the lock. Right? So this is the processor, and I'm going to represent invisible transactions with dashes, and then the refresh transactions as a solid line. So initially, the processor issues the invisible transaction for the lock and the invisible load for the counter. It so happens that the counter returns early. Maybe it's in the second level cache. Huh? Then in the meantime, suppose that I have another processor writing the counter and releasing the lock. We said that these are invisible transactions. So the fact that this counter is written by a processor will not send an invalidation. P1 does not receive an invalidation when somebody writes, because nobody knows that you have a copy. So nothing happens. And then by the time you receive the second request, the response, you see that the lock is free because you get the data that after somebody released the lock, but you have the old count. So that's the problem. Okay? So this is the memory consistency violation. You got the old value of the counter and the new value of the lock. This is not a problem that occurs in current processors, because as soon as somebody writes, you receive an invalidation, and you would squash this load and retry. And by that time, you would read the new value. So that is the problem that we have because of the window of invisibility. How do we solve the problem? How do we make the load visible while maintaining consistency? Well, what we need to do is this refresh transaction, which we're going to call a validation, has to be issued after the load becomes visible. So you issue the visibility, the validation request for the counter, for the lock first, and then the counter. And then as the data comes back, this data is the one that you update all the cache coherence protocol and brings it, and you bring it into the L1. And then you compare the data that you bring with the one that you had in the speculative buffer. If it's the same, fine. If it's different, then you squash it because you have violated the memory model. Okay? So what we do here is we bring the line. In the case of the lock, you saw the correct value, so no problem. In the case of the counter, you saw the old value, you compare what you had in the speculative buffer, it's different, you squash it. Okay? So we squash later than a regular process. Now you might say that this is a dummy solution because you issued the load invisibly first, trying to save time, and now at the end you have to reissue the request, wait for the data to come back, compare, and squash or not. It turns out that many, or maybe most requests, you don't need to send this validation. You can send a cheaper transaction called an exposure. Okay, what's the exposure? An exposure will be a much cheaper transaction that you can send if this particular load had no risk of violating the memory consistency. Okay? So here is an example. Suppose I had a single load that is the older load in the buffer. If you issue the load, it doesn't matter if somebody else wrote later and you didn't see it. Suppose this is what happened. You issued the load, somebody else wrote, and you ignored the invalidation because you didn't see it. That's fine. Because it is as if the load had happened all the way before the write. And receiving an invalidation would not squash this load anyway. Okay? So we can ignore the invalidation. Then at the visibility point, we're going to issue a second request and retire the load right away. The load simply says, send me the correct data, and retires. And the data will come. It will not be compared against what we had in the speculative buffer, and it will go directly into the cache. So all we have to do is basically send a request and bring the correct data into the cache and retire the load right away. So that's what we do, and you can see that we don't need to stop. When the load becomes visible, boom, issue the validation, that now it's called an exposure, and retire. So this is, as you can see, we needed some insights from the part of the security people that told us you cannot change any of the states. We looked at many of the problems of speculative attacks, and we developed this hardware. It's an example of collaboration between the two teams. And there are many works that look at similar problems, and many of the authors are probably in this audience. There's lots of opportunity of doing interdisciplinary research that combines expertise in security and expertise in hardware. We are continuing this work now with looking at software changes. All these techniques that I explained rely on hardware changes only, but there is all this domain of software that can augment and replace some of the hardware techniques that we have discussed. Okay? I'm not going to give you more hints because we're working on it, but so you can think about testing, compilers, and so on. Right? So lots of work to be done here. I would like to move on now to a second idea that came up of this joint work. This is the idea of replay attacks. So what's the context of the replay attacks? As architects, we know that processors can force an instruction to re-execute, correct? So this is a reorder buffer, and we have some yellow instructions close to the head of the reorder buffer. Then we have a blue instruction that suffered an exception, and then we have a bunch of orange instructions that follow. Now, as architects, we know that when the instruction that suffered the exception reaches the head of the reorder buffer, it will be squashed, and then all the other instructions will be gone, and then you're going to re-execute them, right? You're going to bring back the blue instruction and the orange instructions. And this can happen because of page faults, various exceptions, and branch restrictions, and so on, we said, right? People in security told us, but wait a second. If you can have an instruction replay multiple times, that's a huge security opening. Because what you could do is the following, what we call microarchitecture replay attacks. What's the idea? Well, the attacker could force a given instruction to be squashed multiple times, and then at the same time, the attacker could monitor the side effects of all the instructions that follow it. Are they accessing the cache? What addresses? Are they accessing certain functional units? What functional units? These are instructions that are supposed to execute only once. But because of this trick of the reorder buffer, we can replay many, many times. Let's see how we can do this. So the head is the instruction. The blue instruction is the one that will suffer the exception. We're going to wait until the instruction reaches the head. In the meantime, the attacker is monitoring all the orange instructions. Instructions get squashed and then replayed, and then again the attacker monitors all these instructions that follow. These are microarchitectural replay attacks. And we just, at this point, starting to understand the power of this thing. So, let's look at an example. And this example is what we call the microscope. Microscope uses page faults as the instance or the example of reason to replay an instruction, page faults. Okay? In fact, the bad actor here, the attacker, is the operating system. The operating system, what it will do is it will pretend to fix a page fault. But instead of fixing the page fault, it will forget to set the bit in the page tables that says that the page has been brought in. So every time it's going to create a page fault, pretend to fix it, but not fix it. Okay? So this is an environment that is plausible, and we actually did it for the Intel SGX environment. Okay? And this required a lot of expertise in operating systems because we had to understand how the OS interacts with the page tables. Okay? So the attacker is the OS in red color, the victim is in white, and the attacker is the monitor also in red. So initially, the OS sets up the attack. And then we have this load instruction that the OS has marked as having a page fault. Right? So we issue the load, it suffers a TLB miss, it goes to the page walk, and so on. And in the meantime, the orange instructions fill the pipeline, and the attacker is monitoring from another process, could be another context in a SMT processor, or maybe from another processor, it watches the addresses that go into the bus. Then eventually, the operating system is invoked because the load reaches the head of the reorder buffer. It squashes, everything gets squashed. It pretends to fix the page fault, but it doesn't. And then we go back and repeat this thing. And we repeat this as many times as we want to figure out what these instructions are doing. Let me give you a very simple example of what you can do. In this case, what we want is to figure out if a single instruction that the victim issues is a division or a multiplication. Okay? This is called the port contention attack. You're monitoring the functional unit that does division and the one that does multiplication to see if somebody else, if the victim is actually using it. Okay? So this is the victim code. All it does is it does a load, and then there's an if statement based on a secret that either multiplies or divides. And I want to know if it multiplied or divided. Very simple. The attacker, all he needs to do is to keep issuing divisions and timing them. Right? Time the divisions. This is an attack that occurs in two contexts of an SMT processor. So, if the victim threat is such that it uses the multiplier functional unit, so the if statement is do the multiplication, then it will use the multiplier functional unit. And therefore, the attacker, when it does all the divisions, will never see any contention for the divider. Remember that this happens repeatedly because I'm squashing the load and re-executing, squashing the load, re-executing. If instead the victim does the division, then I'm going to notice on the attacker side that the divisions take longer because they have to contend for this victim. So to summarize then, the attacker finds out if a single victim instruction is a multiply or a divide, and therefore it can deduce the secret. So this is just an example of how you can use microarchitectural replay attacks, and it was used just using page faults. But you can think of many different attacks that you can do with this, and defenses. Okay? So again, this benefited a lot with discussions with the security folks. And what we are doing now is we said, well, you can capture a set of instructions inside the reorder buffer, and you can continuously replay those instructions. Wouldn't this be really a neat idea to have a debugging tool or a testing tool around this idea? Right? So we use this for software, we plan to use this, or somebody could use this for software debugging. So we could capture in the reorder buffer a set of instructions that contain a software bug. This could be a very difficult to find bug, could be maybe a data raise that happens very rarely, and eventually you capture it here. And now you can replay it as many times as you want, trying to understand how you got there, what are the values of the different things. So this is another example of how you can do interdisciplinary work that builds on maybe some architecture inside, security, and now some software debugging. Okay? So that's what we are doing at this point, applying this technique, the microarchitectural replay attacks, to software debugging. In the rest of the talk now, I'm going to change gears and look at another problem that will perhaps also illustrate the benefits of working with other people. So the idea here will be a different approach, a different area, redesigning virtual memory translation. So I'm going to start with the same thing. What do architects know about? What is the thing that we know about? We know what caches, right? We know what caches, we know what TLBs. And we also know that there are some new workloads that are very popular today, which are very lightweight virtual machines called containers and environments that use function as a service. So talking to my colleagues in operating systems, they said, you know, all these workloads are putting tremendous stress on the TLB and in the page tables. Can we work together and see if we can figure out a way to redesign the page tables and the TLBs for this type of workloads? Okay. So we decided to work together and rethink the way page tables are designed. Okay. And this work is done with Professor Tianyin Xu, who is an operating systems professor at UIUC, and with Dimitrios and Apostolos. To give you some background on this, I'm sure that most of you know this, but it's a repeat, but let me just say it anyway, is that virtual memory uses TLBs, right, to translate from virtual to physical addresses. So here I have a processor, a core, multiple levels of caches, and we have the page tables that we need in the main memory, right? Virtual to physical translation. And we have a TLB, which is a cache of these translations. Whenever a processor issues a load, first it checks the TLB to see what's the physical address of this load, right? If the TLB misses, I have to go to memory, get the page tables, bring them back here, and then retry the access and proceed, access memory. Well, not so easy. In reality, if you look at real processors today, they use a very complicated system. Okay? So x86, for example, uses what is called radix page tables, which is a hierarchy of page tables. Okay? So here is the idea. When you see a virtual address and you want to translate it, the hardware goes through many steps. The first one is it takes the top 9 bits and it uses this top 9 bits to index into the first level page tables. In this first level, the base is given by a register called CR3. Okay? So you index there, and you get an entry, PGD. This entry is the base of the second page table, second level of page tables. Okay? So you have to have an indirection there, grab the base, and then add it to the next 9 bits of the virtual address. You get an entry in this table, use it as an indirect. This is the base of the next table, add it with the offset, and so on until the 4th level where you get the TLB translations. Okay? So this is what happens today, 4 levels of translation. So here is what happens. You suffer a TLB miss, you go to memory in hardware, grab this translation. Then you do an indirection through this, you go to memory again, grab the next level. This is done in hardware. Then next level, you grab it, next level, and so on until you get the translation. And then you can access memory. Right? To minimize the overhead of this humongously complex process, architects have built L2 TLBs to be able to hold more of these translations close to the processor. They have even added an MMU cache, memory management unit cache, that caches some of these end-to-end translations, so we don't have to go to memory so many times. And even they allow the caching of these translations in the caches, so that when you miss in the TLB, you don't have to go to memory. Maybe you go to the cache and you find the thing you want. This is still quite slow, but it's about to get much slower. Why? Because we're going to get non-volatile memory. And with non-volatile memory, we're going to be able to increase a lot the amount of main memory that we have in a machine, which means we're going to have a lot more translations, a lot more pressure. Case in point, the new Intel processor, Sunny Cove, introduces a 5th level of page tables. Well, clearly, both OS and architects know that it's time to rethink virtual memory translation. Current radix page tables are not scalable. They cannot continue like this for much longer. So we sat together and we said, how can we address this problem? The alternative to radix page tables is to have a global hashed page table. This is what Intel and IBM used to have in the past. So the idea is to have a single global page, and every time a processor issues a request, you take the virtual page number, you hash it, and you go into this table that contains the physical page number. So that seems easy enough. But what's the problem? Big problem. Collisions. Another virtual page number with the same hash maps to the same place. So what do? I need to handle collisions. Now, what IBM and Intel did is whenever there's a collision, you invoke the operating system. So that's a big problem. Something that is supposed to be done in hardware very quickly, now we have collision, we have to invoke the operating system, come in, figure out, no, this is not the one I want the next one. What this thing? So no good. That's one problem. Second, many times two different processes want to share from two different virtual addresses the same physical address. Right? So I have another process here that wants to share using a different virtual page number the same physical. Well, we cannot do this because using this hash, it goes to a different place. So how do we solve this problem? A level of indirection. So this is what we do. So we have to, wherever the hash brings us, have another indirection to the place where it will contain, this thing will contain the actual physical page number, and use this. So we have a problem. And then there's also the other effect, which is, as you may know, that current processors support multiple page sizes. 4 kilobyte pages, 2 megabyte pages, 1 gigabyte pages, so you also need indirection to handle this case. So lots of problems, collisions, page sharing, page sizes, and what happened is this is a dead end, and basically they switched to radix page tables. So that's why Intel went back to radix page tables. So what do? We thought about this, and we came up with something that we call elastic Cuckoo page tables. And it's a way to rethink virtual memory translation for parallelism. So as computer architects, we know that processors nowadays are very wide. They can issue many loads in parallel. It doesn't make sense to have this model where you issue a load, you have to wait for data to come back, then another load, wait, and so on. The hardware really is not designed for this sort of thing. The hardware can do much better. So let's look at how we do this thing. And to explain this, I have to go over what's called Cuckoo Hash. So bear with me, I'll explain what Cuckoo hashing is and then move on to the idea. So with Cuckoo hashing is a way to organize a hash table where each way of a hash table is accessed with a different hash function. Okay, so we have here a deity Cuckoo hash table. Okay, deity because I have D ways, and each way will have a different hash function. So in this case, I want to have P, I want to look up P, and then I'm going to have a hash for each way, and I access the different ways, and if I hit, I find it, in this case, in the first way. But what's interesting with Cuckoo hashing is how you handle insertions. Insertions are done in a way that you can eliminate collisions, and that's the key. You're going to eliminate collisions and therefore open the path to having global hash tables, a way to build page tables. Okay, so how does Cuckoo hashing work for insertions? You pick one way randomly with the hash, the correct hash, and then you find the entry that you want. If the entry is taken, you evict what you have and you put it here. Exactly like the cuckoo bird does, it takes the nest of some other bird that doesn't know about it. Right? So then you take F and you pick another way and you hash it and you evict what's there, you put it, then you take what you evict and eventually you find hopefully a spot. So you can see that if the occupancy of the Cuckoo hash table is below a certain level, even though you may have some of these collision Cuckoo replacements, eventually the thing is able to be inserted. So I eliminate collisions by keeping the occupancy relatively low. So collisions are solved if we use this thing. Okay, so collisions, this thing. How do we handle page sharing and page sizes? We have to have a per process page table. Okay, per process Cuckoo page tables. So let's look at this thing here. The first problem of having per process Cuckoo page tables is that we cannot have them too big, because if you have the page tables too big, right, then you fill the whole memory right away. Remember that the alternative, which is the hierarchical thing, what you do is you have a hierarchy and therefore you consume less space. Here you would consume the whole space every time. As a result, we have to start with small pages and dynamically resize them as the program executes. So we start with small page tables for a process. As the process grows, it starts building up. We augment the pages, the page tables, and so on, right? This is called dynamically resizing. We start here, and then we move to the next one. What do we do when we need to resize? One approach would be to rehash all the entries in one shot, okay? But this is a very costly proposition. Stop the program, copy all the entries from the old hash table to the new hash table. That's going to take a long time to do this. So we don't want to do that. Instead, we want to do what's called gradual rehashing. That means when we're about to overflow a page table, we allocate a bigger one, but we don't stop the program. Okay? We gradually move entries from the old one to the new one as the program runs. Okay? That's what we want to do, gradual rehashing. But this is a challenging thing to do. For example, every time we insert an entry to the hash table, we take the time to move one entry from the old hash table to the new hash table. Okay? We rehash. This is called rehashing. We do gradual rehashing. So for example, in this case, I have reached the occupancy, the limit occupancy of the old page tables, and I allocate the bigger page tables. And then I decide to move M from the old one to the new one. So I take M and I rehash it into the new page tables in the same way as what it used to be, and I put it here. So this looks fine. You can do this as the program runs, but there is one inconvenient thing, which is, what if I want to look up an element while I am rehashing? Well, I need to look up all the ways of the old one and all the ways of the new one, because I don't know if this value M that I'm looking for used to be there or is in here. Right? So that's a problem. That's a concern, that you would have to double the number of lookups to look up an element while you're doing rehashing. To solve this problem, we came up with rehashing pointers. What's the idea of a rehashing pointer? Each of the ways of the old table will have a pointer that will move down as we move entries from the old one to the new table. Okay? So for example, suppose that I'm moving M from the old table to the new table. Okay, I move M, and I'm moving P1 down, leaving behind an area that we call the migrated region. We know that there is nothing there. Right? So then, suppose that I move M here, and then I move on, and I move K and B, and you can see that I'm growing as I move entries. As I rehash entries, I'm moving the pointer slowly down. But that's the key, because then, if I need to insert a value, suppose I need to insert M, the algorithm is very simple. I take M, I generate the hashes for each way of the old tables, I compare the resulting hash against the current value of the piece of the rehashing pointers. And if the value is above the rehashing pointer, I know that the value cannot be there, because if it was there, I already moved it. Right? So in this case, suppose that both for the first and the third way, the value that the hash returns is above the rehashing pointer. In this case, I'm not going to bother do this, and I'm going to check instead the new table. So with the rehashing pointers, the bottom line is that I only need to do D lookups, even while I am resizing the page. Okay, so that's the key. Eventually, that is the key that allows you to do this dynamically. That's why we call this elastic Cuckoo hashing. It's an environment where you start with small page tables and elastically you grow them as the program increases and potentially decrease the page tables, right? And you can do this dynamically while the program is running and never require more than D accesses to the hash tables. Okay? So this is the key idea, and now from here is all downhill. You have this DRE Cuckoo hash table. Okay, you build the hash table this way, and you can see that there is no sequential walk at all, unlike radix. At most, you do accesses, D accesses all the time, and you leverage this multiple issue out of order processors that are current today, because you do N accesses. So this is the table, and in fact, we're going to have one of these page tables for each of the page sizes supported by the processor. So we can have 4K, one for 2 megabytes, and one for 1 gigabyte. Okay, in fact, with this design, you're not limited to 4 kilobytes, 2 megabytes, 1 gigabyte. You can use any values you want. Okay, you may say, well, if you have too many types of pages, then you do many accesses in parallel. That would be too much. Well, in fact, we have something called the MMU cache. An MMU cache will prune some of this. The MMU cache will learn where the entries are, and then before trying to issue the requests to the page tables, it will say, don't bother checking these two page sizes because I know it's not this one, the one you want, right? So we eliminate this. And even in here, it may say, only this way can have it. Okay, so the bottom line is that you can reduce with this MMU cache the number of parallel accesses. So to recap, with elastic Cuckoo page tables, we got insights from the operating system areas on what is the problem of current page tables, existing solutions, past solutions, and we were able to rethink virtual memory translation for parallelism with efficient resizing of Cuckoo hash tables, leveraging wide issue processors that we know is what we have today. Having the sequential access is very costly for current processors, and an MMU cache to prune the search space. This came from a collaboration between architecture and OS researchers, and we are at this point augmenting this work by looking at how to completely redesign the operating system, or at least the parts of the operating system that deal with memory management for hash page tables. Many of the current structure of the OS can be thrown away and redesigned for this thing. So this was another example, and I guess I could continue to talk, but I will stop very soon. I would like to finish by kind of reiterating the takeaway of this talk, which is, let's build interdisciplinary research teams. For me, it has been a very good experience. I have learned a lot by talking to security experts and operating system experts. Let's go and find 1 or 2 faculty in our institutions that have complementary research expertise, because it's the most impactful research. As I said, you can find a problem that nobody can work on, and also is very cost effective. And so here is an assistant professor that suddenly gets an idea and goes off and speaks with his colleague about this, and they start a new proposal, right? And this is a full professor who is trying to get an idea. So even for full professors, it's possible to have something to contribute in these teams. Okay, this is the end. Thank you very much. And I'm going to leave you with this idea.
So we have some about 8 minutes or so for Q&A. Please raise your hand, and then we'll pass the microphone to you.
Yes, very nice talk, Joseph.
Thank you.
Very clear. I'm Mary Lee Southern from the University of Virginia. My concern with all of the interdisciplinary research and all the funding that's going to that we may be losing the core areas of computer science and the core research that we need to do. And so, for example, your work was built on security problems, but does it apply to anything else? So I'm worried about the generality of the research that we're doing now and what's happening to the core areas. And are we doing research in the core areas?
Well, I'm not sure what I can answer. I agree with you that the core is very important. It's really alarming, the trends in funding. I'd encourage you to go and check the websites of the funding agencies. It's a big issue that the core is getting hollowed out. It's true.
Yes, but especially in the university, I should hope that we're doing research that we think is important and not only based on funding.
Hello, I'm Georgie here from Configura, Sweden. I wanted to ask about your work on the Spectre protections. So you brought up this speculative buffer. Would there not be a next level speculative attack on the buffer itself, basically making the presence or absence of some data in that buffer visible through speculating on the speculations themselves?
Yes, every time you come up with a solution, there is some other problem that occurs, okay? But answering, so that's what makes security so interesting, because every time you add a hardware structure or a software thing, you open up more problems, right? In this case, what you need to make sure is that no speculative instruction is accelerated by a more speculative instruction, right? So more speculative instructions cannot, say, allocate an entry in the buffer that a less speculative instruction uses, right?
Makes sense, thank you.
Hi, thank you for your talk. My name is Ye Zhi. I have a question about, in the first topic you mentioned about the security. We are better to not touch the TLB state, but in your second topic you said we need to rethinking to design the new TLB. And also the map size is a problem. I noticed the second idea is also store the map into the memory, and it's in the non-long-time memory. But the parallel hashing function may increase the write pressure to the NVM. It will decrease the lifetime. So can you answer these two questions? Thank you.
Do you mean the fact that we update the page table?
Yeah. The page table is stored in the memory, right? So
right.
This update will decrease the NVM's lifetime.
Okay. One would hope that you don't write to the page table so frequently that you affect the lifetime of the memory location.
Okay, and my first question is, what about the security? Because we are not allowed to touch to the TLB state.
Security issues, I didn't address it in the second talk, the second part of the talk. I'm sure there are many concerns about how you do this, especially if you share and so on. But I didn't talk about this.
Nice talk, Joseph. See, the interdisciplinary that you're talking about actually is two disciplines within computer science itself, right? The truly interdisciplinary is like CA plus bio or CA plus something across the campus, right? Do you think our program committees are equipped to sort of review such papers and pass good judgment on it?
What do I know? I don't know. So we are certainly pushed to some extent to work even further than this, right? Into health and other things that are farther from computer science. There is good reasons for that. So you find good projects there. Many challenges occur, right? So reviewing is one challenge. Second is really finding the right collaborators and speaking the right language. So I don't want to get into this, but this is of course a big problem, an important problem, to do relevant work across disciplines that are far.
Any more questions? All right, let's thank Joseph.
Thank you.